Welcome everyone. So in the last lecture we studied about why we need gravitation. The importance of gravitation, right? It's a force that binds everything together. So it's a force which is attracting moon towards the earth. It's a force which is attracting planets towards the sun. It's a force which is keeping us on the earth, right? Whenever we throw anything upwards, we talked about that, like whenever we throw anything in the sky, the gravitation is the force which brings it back. Now, what we will do in this lecture, we will try to derive a formula so that we can calculate this force. Okay. So for that, assume we have two objects, and they have the masses m1 and m2. Okay, the distance between them is d, and the force we are trying to calculate between them is F. Now we know that since every two objects have a gravitation force which is attractive in nature, so M1 is pulling M2 and M2 is pulling M1, right, with the force F. Alright, so the very first part of the formula is that this force, which is the gravitation force, is proportional to masses of the two objects. So the force F, which is acting between this M1 and M2, is proportional to the product of their masses. So force is proportional to product of their masses. Okay. So if I have two heavy objects, the force would be much higher than the two light objects. Okay. Second thing is this force is the force is inversely proportional to the square of the distance. Okay. So the farther the objects are, the lesser is the force, right? So the force between Earth and Sun and force between Sun and Pluto is different because the separation is different. The mass is also different because Pluto is different mass than Earth, right? But just because of the separation, the force would be smaller compared to Earth. Okay, so if I combine these two equations, what I get is force is proportional to product of their masses and inversely proportional to the square of their distance. Okay, now if I take out the constant of proportionality, I can say force is proportional to some constant g, and that g is very important. We will talk about that, but for a moment it is a constant of proportionality. So g and then m1 m2 divided by separation square. This formula, it's amazing. Okay, it gives you idea about force between any two objects, the gravitational force between any two objects. It's a calculate the force between Sun and the Earth, Sun and the Pluto, Sun and Mercury. So those are like really massive objects, right? At the same time, it gives you a force between two small objects. Like say I have two books on my table and I'm trying to calculate the attractive gravitation force between the 10. So this formula, it's just blows your mind, right? Now let's talk about the G. I said like G is very important. G is constant proportionality. So G, we know, is a constant, right? It's a constant of proportionality. Okay. Now another term for G is it's also called gravitation constant. Gravitation constant. Okay. Now, I want you guys to understand this because the gravitation constant, what it means is a constant which is basically tells me that the value of G when I'm calculating the force between Sun and Earth, it's the same value of the G I would be using if I'm calculating the force between Sun and Earth or Earth and Moon. Now these are like amazingly massive objects, like it's amazing, but at the same time I would use the same value of the G if I'm calculating the gravitation force between two books on my table. right? So it's the same value of the G. Okay. Now, the unit of the G, that's another point here. So unit of the G, I'm gonna the same color here. Now, our previous formula, we have F equal to G m1 m2 by d square, right? I can rearrange this formula to get F G equal to F d square divided by m1 m2. Okay. Now, if I put the SI units of force, which is Newton, distance, which is meter square here, divided by masses, which is kilogram into kilogram, right? So SI unit I get of G is Newton meter square in kg minus 2. This is a SI unit. Okay. And the last is the value of the G. So in, I believe somewhere between 1750 or 60, I don't recall exact date here, but Henry Cavendish was the person who was doing some experiments and calculated the value of the G. So the value of the G is 6.673 into 10 to power minus 11. It's a very small value, right? Newton meter square kg minus 2 units. So it's amazingly small value, right? It's 6.673 into 10 to the power minus 11 Newton meter square per kg square. Okay, so we discussed 4 things here. It's a constant proportionality. G is also called gravitation constant, SI unit of G, and the value of the G. Now let's do a problem to understand this more. Okay, so the problem is, they're telling us mass of Earth is 6 into 10 to the power 24 kg, and the moon is 7.4 into 10 to the power 22 kg, and they are giving us the separation between Earth and moon is 3.84 into 10 to the power 5 kilometers. Then it's asking us calculate the force which is exerted by the Earth on the moon. Okay, so we have 2 objects here. So we have Earth, and then we have moon. We have m1 here, m2 here, and then there is a separation between the center of the Earth, center of the moon, that is D, and there is a force which is attracting Earth towards the moon, moon towards the Earth. Both would be the same in magnitude. It's asking us to calculate the force. Okay, now, so we know force is equal to G m1 m2 by d square, right? So we know m1 is the mass of the Earth, which is this. We know m2 is the mass of the moon, which is here. It's also we need the value of the d, which is separation, which is also provided. And the fourth thing we need is the value of the G. Now we know Henry gave us the value of the G, 6.673, but in the problem they're saying that instead of that, use this approximate value of G, which is 6.7 instead of 6.67. So in problems like this, use the value of the G which is provided. Okay, so if you put all these values together, so the G would be 6.7 10 to the power minus 11. Okay, and then multiplied by m1, which is mass of the Earth, so 6 into 10 to the power 24. Mass of the moon, which is 7.4 into 10 to the power 22, divided by separation. Now the unit of separation here is kilometer, and our SI unit we know is meter. And just to be, so we will use the same unit here. So I will convert 3.84 into 10 to the power 5. Now this is in kilometers. I will just multiply this by 1000. So now it is in meter, right? Now I need to take a square of this because in the bottom we have square of distance. So that would be the value of the force. So if you do all this together, I think number you get is 2.01 into 10 to the power 20 Newton. So that's a force. That's a huge force. If you look at it, it is 10 to the power 20. That's like amazingly big number. That is the amount of force which is exerted by the Earth to keep the moon in that motion. Okay, if let's say if this force somehow becomes zero, okay, then the moon will just fly off. So that is the amount of the force that Earth has to exert on the moon to keep it close. I hope you guys understand this problem. Go over this lecture one more time just to clear your concepts.